Like we've got everyone in from the waiting room, so let's go ahead and get started. So hello and welcome to the Ask Echometer weekly training session. Today's session is on dynamometer analysis, titled Examples of Forces Not Accounted For by the Wave Equation, and it will be presented by Lynn Rowlan. During his 40 years in the oil and gas industry, Lynn has received several awards for his work. He's authored more than 80 research and technical papers, and co-authored a book on gas well deliquification, and holds a patent on plunger lift analysis. He's given hundreds of seminars and talks on efficient operation, optimization, and troubleshooting oil and gas wells. And so we're so glad he's presenting today. So Lynn, I'll go ahead and turn it over to you now.
Thanks, Carrie Ann. This presentation came from customers sending us data that was showing large amounts of mechanical friction, and the mechanical friction was typically coming from drilling horizontal wells with dog legs, horizontal wells where the pump is set down in the curved section or down the horizontal section of the well. So we started talking about it, probably several years ago, and then we've written a couple of papers. Both of these papers are listed on the screen. One paper, Lynn Rowlan, Clint Haskins, Carrie Ann Taylor, and Ken Skinner were authors, and then Norm Hine and I wrote a second paper. So those papers are listed on the screen here, and they'll be available for download on our webpage. Carrie Ann also mentioned that this presentation will be recorded, and so that'll also be available on our support Ask Echometer webpage. The forces that are accounted for by the wave equation, typically the wave equation, when I think about it, is there's been several wave equations published that try to account for deviated wellbore, but the vertical wave equation that's somewhat simple doesn't really have a term in it for contact between the rods and the tubing or any kind of friction forces other than the fluid acting on the rods. And so the friction typically is a function of the velocity of the rods. And so when you talk about mechanical friction, you talk about as a function of velocity, whereas mechanical friction typically isn't a function of velocity. It's more of a drag coefficient. So we're going to talk about the idea that the rods, when they're in the curved section well, they're resting on the side of the tubing, and that has an impact. And if you're using a vertical wave equation, that typically is not accounted for. We're going to show an example of an overtight stuffing box. We're going to show sticking down hole. We're going to talk about mechanical friction from paraffin. But we're not going to really talk much about the simple, normal idea of rods contacting the tubing and there being a certain friction force. We're going to talk about these. We're going to. That one's pretty easy. You just put in a deviation angle, and you put in your normal force, and you can calculate some expected friction. But most of those frictions, I don't think we see that much. So we'll talk about other mechanical frictions typically. So when you have mechanical friction down hole, you know that you have it because you see an increase in rod loading at the surface of the well that you measure. It's not really modeled in some cases how it's applied. The frictional excess forces result in additional horsepower being displayed, which means the dynamometer card gets larger in area, and you have higher peak loads and lower minimum loads but we're typically assuming that the friction force comes from the rod and tubing sliding along the tubing. What we see often is we see the plunger velocity when downhole sticking becomes a problem go to zero, and that can happen during the upstroke or the downstroke. And we're going to talk about this idea of the relationship between plunger velocity or velocity downhole with respect to a sticking force, and that's something that that we'll see several examples of. The rod string has a length and a diameter, and typically it's made up of more than one rod and more than one type of rod. Some fiberglass, some carbon fiber, some steel typically, and all those have different modulus elasticity, different amounts of stretch coefficients, which is called the rod string stretch coefficient, Kr, and we can use that to identify and help us identify the location of the downhole sticking. So this is a fairly simplistic surface dynamometer card. Here's our surface dynamometer card, and here's our pump card. And I show a plot here that says this is the load going up in the position horizontal. It's a change in position horizontally, change in load vertically. And if you take the load and divide it by the change in position, that's the slope of this line, which we call the spring constant of the rod string. And so the slope of this line, when you're not pumping really fast, and you have a lot of additional acceleration and echoes of the motion of the rods, you see the slope of this line representing the stretch of the rods, and they typically are thought to only stretch due to picking up the fluid load. So the height of the pump card is the fluid load. It's the wave equation views the fluid load applied to the bottom of the rod string, and when the rod loading increases here, we're picking up the fluid load being applied by the differential pressure acting across the pump. And that causes the rods, based on their lengths and diameters, to have a certain amount of stretch per pounds per inch. And this represents what we call the pump is the force, and the spring force, the spring coefficient is for the rods, and the distance they stretch is the basic law of physics that the force equals the spring constant times the distance stretched, and that's assuming the rod string's acting like a giant spring. Well, both the rods are long and the tubing is long, and they both in the well tend to act like a spring if they can move and stretch. So often the tubing's anchored, you don't see the tubing movement, but when the tubing is not anchored, you see the pump card show the movement. But on the surface card, you typically see when the tubing's anchored, you see the spring constant in the surface. The slope of the surface card is as you pick up the load here, and then as you release the load at the top of the downstroke. Now this is a plot trying to relate the stretch of the rods to the modulus elasticity. And so when you look at a typical plot of stress versus strain, the stress is usually the force acting on the rods divided by the area, and the strain is a change in length over the length of the rods, and so we'll call that the strain. And the modulus elasticity is a ratio. It's a ratio of the stress divided by the strain, and that's the slope of this line. And that's a property of the rods, so the property of the material. So there's steel moduluses and fiberglass modulus elasticity and other types of materials that have different amounts of stretch versus change in length. Now the idea is that when you apply a certain force, then based on the properties of the rod, it's going to change a certain delta length. And if you double the force, you double the stretch. And so that's the property of this. And as long as the rod is below its yield point, then it's going to be elastic. It can stretch and unstretch, and the rods don't deform. But once you go past the yield stress, the real yield point, then the rods plastically deform, and they have no longer non-elastic change in length, and then they won't return to the original unstretched length if you overstress them or go past their yield point. Now, to come up with the equation for the spring constant, you have to have the area of the rod and the modulus elasticity of the rods, and you divide by the length, and that gives you the spring constant for the rod. And so each taper of the rod, each section has its own spring constant. And so if you're trying to determine the overall spring constant for a rod string, you have to take each individual rod separately, section of rod separately, and add them together to get the total spring constant, and then well, this is it's inverse. See, this is inverse, and so we solve for the Kr of the entire rod string taper, the whole rod string, using this type of equation right here. Now, this equation assumes that the rods are being stretched from the end of the rod string by the pump load, and if the rods are stretched by a shorter length, like it gets stuck right there, then the rod string is more difficult to stretch. It's stiffer, and so if you have a point where the rods stick, then the sticking causes the rod from this point to the surface to stretch, but below that sticking point you don't stretch, and so now you have a different spring constant. And that's important when you look at the surface dynamometer card. I'm going to go back just a second here. The slope changes. This slope changes when you have a sticking point that's not at the pump. So you'll see a change in slope if the sticking point changes to a point that, let's say, is higher up in the rod string. And we'll talk about that more. Now, this is a slide that starts to introduce some sticking. And this pump card shows a downhole problem, and there's no production of surface in this well. And the pump card looks like an upside down shoe. And the spring constant here, based on the rod string in the well, it should be, the slope of the surface card should be along this line, and if you look, the line is much steeper, which indicates that there is a shorter section of the rods that are stretching. So a lot of the presentation we'll talk about is this concept of a surface spring constant not really matching up with the stretch of the rod string that you expect you should have based on the sucker rods that are ran in the well. Now, it's a lot easier to drill a vertical well, and we've kind of stopped as an industry drilling very few vertical wells anymore, and most of the wells that we drill are typically horizontal wells, and that ends up, in some cases, we've been drilling the wells fast to reduce the cost, and the faster we drill it, the typically lower cost. But if you don't control the well and you drill the fast crooked, and that causes a dog leg or a severe change in the wellbore, then that can not only increase the long-term operational cost, but it can start to cause downhole frictional forces, mechanical forces, and in fact can cause downhole sticking. So that's kind of a little introduction to the spring constant and some of the ideas of mechanical forces. And this is the basic way the wave equation handles the damping factor. And the damping factor is in the wave equation, and it represents a frictional force that's acting on the rods, not from the rods on tubing, but from the fluid rubbing on the rods, and that's typically how the horsepower is removed from the surface down to the pump with the damping factor. And so you can see here that this pump card is concave outward, that the damping factor is too low, and this downhole pump card, the damping factor takes out too much friction from the upstroke and too much friction from the downstroke, and it's concave inward, and that means the damping factor is too high. And this pump card right here on the right shows that the load on the upstroke is fairly flat, and the pump load on the downstroke is fairly flat and resting on zero. And you'd say, well, the damping factor is just right. Now, what does that mean, just right? Well, what we're assuming that when we have a constant pressure on top of the plunger and a constant intake pressure on the bottom of the plunger times a constant area, that the pump load that's being carried by the rods is going to be fairly flat or constant because there's no change in the pressure above or below the plunger. And so that's what this pump card load represents. It represents a load that's being applied to the rods by the pump during the upstroke. And this represents the load being applied to the rods on the downstroke. And it should be close to zero because the trailing valve is open. So this is eyeball adjusted, perfect damping factor. And you can kind of tell when it's too much or not enough just by it being concave inward or concave outward. Now, we're also going to have some examples files available, and so this is the name of the file. It's damping underscore 10 API. It's a 10 API gravity crude, and we'll have that online on the Echometer webpage. That you can also download the example TAM files, and we'll talk about those. We'll look through some of these at the end of the class. Now, this is a pump card in the same well. And here you can see the pump card's concave outward on the upstroke and concave outward on the downstroke. And the damping factors here are much lower than the damping factors over here. And the pump card load here is flat on the upstroke and flat on the downstroke. So you'd say, well, these damping factors are probably more accurate because by looking at the pump card, it appears to be the correct shape. And over here, well, the pump card concaved outwards means there's not enough dampening, but the main reason for me to show this is that this data was collected with a clamp-on device that doesn't have, it just measures the diameter change of the polish rod, which is we call the polish rod transducer, and the zero offset comes from setting the pump card on the zero load line of the load measurements with this clamp-on device called the polish rod transducer. And if you don't have the pump card with the correct downhole stroke load, then the shift here we're seeing here also shifts the surface loads acquired, and it's going to make your loads that you use for your polish rod load, your structure load on your pumping unit, and your torque calculations to be too high. Too high on the upstroke and too high on the downstroke by this extra mechanical friction that's not removed by the damping factor, or this extra fluid friction not removed from the rod stream by adjusting the damping factor. All right, now so here this is just showing that it's not quite enough damping, a default, and when you have heavier crude you may have to have a much higher damping factor. We'll see an example of that later. Here's a well that has mechanical friction in the well that's being applied to the rods, and we have a before and after card that are overlaid on top of each other. The blue is before. We can see that we have a decrease in the downstroke loads on the downstroke. We can see that the loads on the upstroke are higher. We can see that the pump card stroke is shorter, and we can see that the area is more in the blue, more horsepower work's being done before, and once the well is treated for, in this case was treated for paraffin with hot water, that the minimum loads in the pump card came up and the pump stroke got longer and the peak load went down and the minimum load came up. And this is an example of some type of mechanical friction. In this case it was paraffin, but it could be scale. It could be over tight stuffing box. It could be a misaligned wellhead with your pump unit horse's head. It could be a crooked place in the well called a dog leg down hole. It could be from wellbore deviation. It could be pump friction, crimp tubing, or some other coarse problems, and that makes the system much less efficient and causes there's additional loss in stroke and additional loads, more horsepower. So there's a lot of penalties you pay for having this extra friction in your well. Now this is a a well with extra paraffin in it. It's out in West Texas near Midland, and it shows that the pump card goes way below the zero load line as required with the Horseshoe load cell. So this is the extra friction on the downstroke. This is the extra friction on the upstroke. The fluid level came up because the pump stroke was reduced. We stopped. This is a valve test here. We're pumping right here, and we stop on the upstroke, and there's a load versus time on the upstroke, and it can't be higher than this dash green line because that's the weight of rods in air plus some and fluid plus the maximum fluid load. So that's what the maximum load line should be, and it's higher than that. Well, this distance higher than that is due to this extra mechanical friction on the rods from this paraffin. And then on the downstroke, when the rods are moving down, then the paraffin friction resists the motions of rods and makes the rods lighter. And so when we stop, we see that this load is less than it can be. The rod string in fluid weighs this dash green line, and it can't be less than that. Well, it can only be less than that if there's some kind of mechanical friction holding up the rods, or there's maybe some rods are missing, but in this case it's paraffin friction holding the rods up. Now this is the same well that has and this is the example of the well name. So when you download this PDF of this file, you can also download the examples and find this example and go through and compare and use this data if you'd like to better understand. But in this well, they would shoot fluid levels on these wells. When they see a high fluid level, they think, well, it's time to hot oil the well because we had the wells that were pumped off, and now the fluid levels come up, and we've lost downhole stroke, and so the paraffin is reducing our downhole stroke. So this is an example where there's no gas flow up the casing. The fluid levels come up high enough to stop the inflow of gas, and the fluid level's high. It should be down deeper, and so it's time to treat the well. Again, here's the paraffin. Loads are high here on the upstroke. When we do a traveling valve test right there, and the standing valve loads are too low. And notice this distance from here to here represents the paraffin on the downstroke. And when you release the brake and the rods start moving backwards down, then that paraffin, the brake was released right there, and that breaks the friction, and that's this distance here is exactly this, pretty close, the same distance right there. And you see almost the same friction on the upstroke and the downstroke due to the paraffin acting opposite of the motion of the rods. So here they were moving up and made the load higher. Here the rods were moving down and made the rod loading lower when you stopped. When you look at the surface dynamometer card, you see a vertical line at the top of the stroke, and that vertical line is the reversal of the mechanical friction. So we're going up right here, and then we turn around and start going down, and that creates a change in the friction opposite the motion of the rods, and so you typically see a vertical line at the top and the bottom. There's a vertical line right there due to the reversal of the direction of the rods because of friction. Mechanical friction acts opposite the motion of the rods. You can see here the pump card shows right there the friction is being released on the downstroke, and that slope right there is directly related to that vertical line right there, and you can't see it, but there's a slope right here, and that relates to that vertical line right there. So when you have mechanical friction that's going to reduce the downhole stroke, tends to make the fluid level come up higher. The friction's opposite direction of the motion of the rods, and that causes you to see a vertical line at the top and the bottom of the stroke on the surface card. The pump card, if you have a lot of mechanical friction, usually goes above the fluid load line. Calculate from the fluid level shot or even the FO max line if you're pumped off, and go below the zero load line. You'll see the standing valve load when you stop to weigh the weight of rods in fluid to be less than the calculated theoretical weight of rods in fluid. And so the unaccounted friction, it impacts the shape of the pump card. It increases the area, which means more horsepower. It reduces the efficiency of the system. All right, so here's a well. We've got an animation of the position in polish rod position in green and the polish rod load in red. Now, if you were to plot a normal well that's pumping properly, you'd see that the load and position wouldn't be 1-for-1. This is a 1-for-1 relationship. And so this is what you would expect to see and what you usually see when you have a pump that's stuck down hole in the bottom of the barrel. And so here the load is increasing load, and then at the top of the stroke, decreasing load. And then on the surface card, you see that the spring constant for this rod string is 190 pounds. And so the stretch of the rods picking up the load follows the 190-pound load, and then it goes right back down the same slope. And so this is an example of a rod string where you're stretching the entire rod string from the pump to the surface. The slope matches, but there's no downhole pump stroke because all of your surface stroke is lost to stretch. So the surface stroke is 64 inches. Okay, 64 inches of surface stroke from here to here. The spring constant is 190 pounds. And so if you take the surface stroke times the spring constant, that's 12,160 pounds. We call that SKR. That's how much of the load has to be applied, increased, when you increase the surface stroke 64 inches. If you lose all that surface stroke to stretch, it takes a force of 12,160 pounds. And this is a typical normal example of a stuck pump in the bottom of the pump barrel. Now, this is close to that previous example, except when this operator came this well, he said, oh gosh, look, I've got all kinds of extra mechanical friction here, and my pump stroke is very short, and so I'm losing a lot of my surface stroke to stretch. And so this is all stretch here on the upstroke and unstretching, and so I've got 18 inches of downhole stroke at your pump. It's only making about 12 barrels a day, and you're losing a stroke due to paraffin. And so once they treated the well, you can see that the blue is the previous data that we just saw. The black is once they've treated the well with for paraffin, and now you have increase of production out to 100 barrels per day versus 10 before. And notice that the pump card just goes up to the height where it should be based on the load calculated from the fluid shot. So this is where you'd like to see your pump card be if you don't have any excessive mechanical friction from paraffin, and that your paraffin treatment was effective. So if you still have load above the FO from the fluid level and load below the zero load line, then there may be some additional friction acting on your well that you didn't take out by your treatment, and maybe you need to treat the well a little bit more or a little bit longer. This is a well up in North Dakota, and this data came from Ken Skinner. I called Ken one day and said, Ken, I'd really like you to go to one of your wells and have a well that has a low fluid level, the pump is full, and then take your crescent wrench and over tighten the stuffing box. And so he put the crescent wrench on the stuffing box at the surface, and he tightened it down until it started to squeal. And now this is the additional horsepower. See, this surface dynamometer card is larger than this before surface dynamometer card, so the extra area is 1.2 horsepower, or 15% more horsepower by just increasing the tightness of the stuffing box. Now, the force he applied was at the surface, at the stuffing box. And when you look at the pump card shows this extra force on the downstroke and this extra force on the upstroke and the downstroke. So you see this extra force here that wasn't applied at the pump. And so the wave equation doesn't know that a force was applied at the polish rod at the stuffing box. And so that extra 1.2 horsepower stays in the wave equation calculations and ends up at the pump. And so that doesn't make much sense. So the horsepower belongs at the surface, not at the pump. And so this extra height on the upstroke and extra height, minimum lower loads on the downstroke indicate extra mechanical friction. What it doesn't indicate is not at the pump. And so the pump card is kind of like the trash can. Any forces that are applied anywhere from the surface of the dynamometer data down to the pump card, the wave equation assumes that the force is being applied at the pump, typically. So we modified the TAM software to add in a stuffing box friction force if you want. And so when you add the stuffing box friction force of 500 pounds, now the pump card looks correct, and the surface card is still too large. But I'm wondering out loud here, if I put this extra stuffing box friction and I don't tell anyone, then it doesn't show a problem, doesn't show excessive friction. So if I go talk to someone, I might want to show this pump card like that and say, look at all this extra friction we've got in the well, and I'm pretty sure it's from the stuffing box. And look, once we adjust the stuffing box friction, let's go out and see if we can't fix this problem just by lubricating the stuffing box and maybe repacking it. Now this is a set of data I got a long time ago, and if you notice and watch this animation here of the plunger in the pump, you'll notice that it stops on the upstroke. And so we're on the downstroke here, trailing valve is carrying the fluid load, and right there it stops. Notice again, let's just watch it. We're on the upstroke, and right there the plunger stops. At that little bitty spike right there, the plunger stops. And so I hadn't seen anything like that before. And so I started saying, I think this indicates sticking downhole. And at first I said, well, it's sticking at the pump. But then I realized that it's not at the pump. And so that was kind of the first step that kind of led us into this presentation we're in. Now, if you look at the plot of the position of the polish rod in red versus the position of the pump in green, you see if we plot the pump position, when the pump position becomes flat, that means it's not moving any. So here's inches. The pump's moving up from 0 to 100, and it stops for 0.6 of a second, while the polish rod moves up another 20 inches. And you take 20 inches times the spring constant, 214, and the polish rod was involved with the tug-of-war with some sticking point downhole, and the 4,000 pounds of force applied at the surface overcame the sticking force downhole, and then allows the plunger to move. And so there's a plunger moving after the sticking force is overcome with this extra stretch of the rod string from the surface down to the pump. No, not the pump, to the sticking force. All right, so Dr. Pody and I were discussing this one day, and we were talking about the spring constant, and one of us said, hey, look, that slope right there and that slope are different. And that means this is a stiffer rods right here that's stretching, and this means it's the spring constant of the entire rod string stretching right there. So I said, I think I want to calculate that. And so we went and calculated the slope of that line, and that means that the rods, if the rod load's applied at that point, and that section of rods is stretching from some point to the surface, it's a shorter section. So then we calculated the spring constant for different lengths from the surface down in the well. And so the spring constant for when the 1,000-foot rods in a well is 2,000. Well, it's 339. If you look right here, 339 means that the rods were sticking. If the entire force was applied at that point, then that would be the force that would be applied to the rods, sticking the rods. And so that would be the sticking point, and that would be the stretch. So, we can now go to the operator and say, let me see your deviation survey, and we'll see a dog leg, but this is old data. I don't even know where it came from. So I can't ask the person that had this data. So now I started looking for more data to see if we could apply this same technique to another well. Now, this is a well that helped me understand that the animation in TAM is important, because you can see that it sticks and it sticks and it sticks. And so this well is in a deviated well bore, probably not very many points, because TWM only had 15 points to define the deviation survey. But if we enter data in TAM, it's unlimited for the deviation, but you can see it's not a straight well bore. And so if you go to the animation and we watch it, we'll see that as the plunger moves up, it stops and it stops and it stops right there. And then it doesn't stick on the downstroke, it just moves on the downstroke, but the pump's full. Now that's kind of weird. And then here on the upstroke stops, and it stops, and every time there's a little spike right there, the pump stops, because that means the velocity of the goes to 0 downhole. Now it stops there, and it stops right there. But now look, it stops different places. Stops, 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 stops on the downstroke. And so this stopping is at a different time interval on the upstroke and the downstroke, which is interesting and sort of surprising. And if you look at this data right here, I'm going to pause it. Notice that the rods are stretching, pick up the fluid load, and the plunger velocity in green goes up, and the plunger moves, and then it stops when the velocity drops to 0. Here's the 0 velocity. It drops to 0. It stops, and the plunger moves, and it stops, and the plunger moves, and it stops. And then on the downstroke, it doesn't seem to stop any at all when the pump's full. But notice here, there's the stroke. That's the top of the stroke, and so this is the time for the upstroke, and this is the time for the downstroke. And so the spacing of the sticking is based on the round trip travel time of the force in the rods. So let's watch here. So it stops right there, stops, and then we go on the downstroke, and the downstroke's time's much longer, so it's much slower, and so we have time for more echoes on the downstroke. So it stops, and it stops, and it stops, then it stops there, and stops there, and stops there, and then it pumps full and doesn't stop anymore. And now we're on the upstroke, stops, stops. Those are sticking points, and now in the downstroke it stops. Anyway, every time it goes to 0, it's stopping on the downstroke. So that's an example of sticking in the well. Now we talk about mechanical friction. There's a term people use, they call it Coulomb friction. And that's the friction that we have when the rods are moving in the well, and there's contact between the rods and some mechanical force, either on the tubing or some kind of thing like paraffin. And that's the kinetic or Coulomb friction. And then there's also a static friction force. And so the static friction force, when you're stopped, is much higher than the moving friction force, the kinetic friction force. And so we really have two forces that we're having to deal with in the rod string that have to do with mechanical friction. One is if the rod stops, then the static friction force takes over. You have to pull harder than you do if the rods aren't stopped, because that's a lower sliding friction force that occurs. So this is a well up in Wyoming. Clint Haskin was involved with writing the first paper, and this is some data he collected on a well. And he sent this data to Echometer and said, look at this well, look at all this extra mechanical friction. And I said, yeah, you acquire this data with the polished rod transducer, and all this friction right here is plotted above the maximum, but probably half of it's on the upstroke and half of it would be plotted on the downstroke, and probably right there, that's where the friction is being released. And so really the friction, these lines should be below the zero load line. And it has a rod string in the well. It's got high strength rods, 1 inch, 7/8, 3/4, 1 inch sinker bar, and then 300 feet of 1.5 inch sinker bars. And a week later, he sent me the data on this well and said, what's wrong with my well? It changed. And he acquired this data with a Horseshoe load cell. He acquired this data with a polished rod transducer. And notice with the Horseshoe load cell, about half of the pump card is below zero, and about half of the pump card is above zero. And the surface loads are centered around the weight of rods and fluid. And you would think that if you're measuring the weight of rods and fluid on average on the upstroke, there's no pump load. And so if there's no pump load, then the pump card should be flat. But the pump card's not flat. And so Clint said, there's no production of surface. And I said, well, I don't think your pump is attached. I think you have a rod part down in your pump, because the average load here is the weight of rods and fluid, but there's no production of surface, and this pump card looks really weird. Looks like an upside down shoe. And so this is the stretch of the rods right here. So here's the stretch of the rods. That's called the spring constant, and we can calculate that as 1,478 pounds. But if all the rods were stretching, the slope of this line should be 142 pounds per inch. And so there's something going on here. It doesn't look like, it looks like a shorter section of rods are stretching. And so there's no production of surface, and we're gonna try to figure this out by removing the rods from the bottom of the rod string toward the surface, and we're going to see how this spring constant changes as we have less and less rods being stretched. And once we get the correct amount of rods attached to the load cell, this rod stretch line will match the stretch of the rods that we measured in the well. So we're going to reduce the rod string until we get this line and that line to match. So that's what we measured, 1,478 pounds. And this is what we calculate based on the entire rod string stretching. Okay, but there's only a shorter section of rods are stretching, since this is much steeper. And so we take off the weight bars, which is 300 foot of 1.5 inch rods, and look, they're missing, and the spring constant's changed from 142 to 143, and it doesn't match. So we need to take off some more rods. And every time we take off some rods, this pump card is going to change shape and move up toward the surface card, and it's going to change shape because we're going to take away the calculations from the wave equation through the rods that we're removing. So now this pump card represents the load that's applied right there. If all the load was applied right there to create this surface dynamometer card. So now we're going to take away some more, which is this 3/4 rods and the 1 inch rod. And notice it's changed some, it's moving up. And now the spring constant is 233. It doesn't match 1,478. And next we're going to take away the 7/8 inch rods, and it still doesn't match. It's getting closer. Now it's 631 versus 478. And all we have left is 1 inch rods. And so we say, well, what if we take away enough rods to make it match? So we take away about half the rod string. And at 1350, it matches exactly. We calculate the spring constant for, well, it's not within one pound per inch. Exactly, it matches 1479 versus 1478. So we say, aha, we know that the rods are sticking at 1,350 feet from the surface. And so I knew who had this well, so I said, Clint, can you send me the deviation survey, because I think there's a bad dog leg at 1,350 feet from the surface. He said, sure. So here is the deviation survey, and sure enough, there's a dog leg severity calculation, and right there at 1,371 feet, exactly the same depth, well, pretty close, is a 2 degree dog leg. And that 2 degree dog leg was causing all that mechanical friction. So that's a problem. That's a problem that's causing the rods to stick. Now, when we plot the spring constant in this well versus depth, the program calculated, so all I did is just take off those points and plot them in Excel, and there's the plot of the spring constant versus depth. And here's the deviation survey. And the old rule of thumb is if you have a dog leg between 0 and 3 degrees dog leg, that's okay. Don't worry about that. Well, that only applies to wells that are typically less than, I don't know, 6,000 foot deep. And so we didn't change the rule of thumb. When we started drilling wells down 10,000 feet in horizontal wells, we didn't change that rule of thumb. The rule of thumb isn't any good anymore because in this well, a dog leg of 2 degrees at 1,371 feet resulted in an excessive amount of friction that causes severe downhole sticking. Well, here's another well. Looks kind of the same. Look, this pump card goes backwards. What's this backward slope? What's the backward slope? Well, let's go back over here. Look, that's got backward slope. This is backward slope. Where'd the backward slope come from? Well, the wave equation knows how to calculate the forces down the rod string. And so this force at the bottom of the rods right there is required to calculate that force with the wave equation from the surface. So the surface force is that, and the only way that surface force can look like that is if there's a force like that at the pump. Well, there wasn't a force like that at the pump. There was a force like this at 1,350 feet from the surface, about a 10,000 pound friction force acting on the rods. A 10,000 friction force acting on 1,350 feet of rods made that load at the surface. Oh, so in this well, this backward slope is being calculated incorrectly from this force at the surface right there acting at the pump. It's not at the pump. It's somewhere else. Where else is it? Well, I know the slope of that line, and this isn't real. And so if I start reducing my rod string, this backward slope is going to become vertical at my sticking point depth. And so what is this slope? Well, let's go find the slope. So there's the slope, and then there's our deviation survey. It's got a lot of deviation dog legs at 2,700 feet. And so I only leave the rods down to 27 feet, 1-inch rods, and the slope of this line is 726 pounds per inch. It matches up with the dynamometer card, surface card, and it says that there's a 7,000 pound mechanical friction force acting on the rods at 2,750 feet, because now we have a dog leg of, well, this is measured every 100 feet. So this is an average dog leg of 3.7 and 2.25 at 27 feet from the surface. And once we use 2750 for the length of the sticking point, we can get the slope of this line to match the measure loads, and we can see a vertical line here where the friction force is being applied. Oh. Well, they have a dog leg right there, and this is near the surface. Why did they have to drill a crooked well like that? Because they need the production quick to have the income close to the time they drill the well. The investors from maybe New York City told them to drill the well fast and not drill it for a long life or drill it for low operating cost. So here, when they're operating the well in this dog leg, the tubing has wall loss up to 50% wall loss at 2,700 feet. So this is another example. This was used with the PRT data. So when you see a pump card that's leaning backwards like this, that's usually because the wave equation didn't know what to do with the unusual mechanical forces at the surface, and it assumes that the force is applied to the pump, at the trash can, at the pump. And so this is the forces that are calculated at the pump that would create this force here at the surface and that force at the surface. This is a wave equation doing that because it doesn't know what to do. It doesn't know where the mechanical force is being applied. The sticking force. All right, let's go on. So what we've talked about is the rods stretch due to fluid load. That's normal. And the rods have a spring constant based on the rod string design, and they act like a giant spring. But the rods also can stretch to overcome mechanical friction, and we've seen that. We've seen that when you treat the well for mechanical friction, things like paraffin, if the treatment's effective, you should see a change in the rod loading, the pump stroke, and the horsepower. The dogleg severity and the Steffenbach friction are mechanical friction forces that are applied at a point, not the way we model mechanical friction in the deviated wellbore model as rod on tubing sliding mechanical friction with a drag coefficient. So the wave equation will calculate it says extremely unusual, but I like to say ugly pump card. When the mechanical forces are not applied at the pump and they're applied somewhere else in the rod string. Now, what this tells me is that there should be limits for drilling wells and not drilling crooked. So there should be some kind of limitations on dogleg severity not provided by New York City, the stock market, but it should be applied for operating suck rod lifted wells efficiently and long life. And we should avoid dog legs near the surface of the well. Now, this is the reference out of this paper, and the paper is also on the first page. And the original idea was that we would have trouble-free operation by having some rule of thumb limits. Usually the wells were less than 5,000 feet. And we measured the change in angle over 100 degrees per 100-foot stations. And we've added some new recommendations in this paper based on some of the data that we've seen. And so the old rule of thumb was that from 0 to 3 there was no problem. Well, that's not true. That's a bunch of cussing and hollering right there. It said, the old rule said from 3 to 5 you have increased wear and friction, and then for greater than 5 degrees you'll have problems. But it really depends on where the dog leg is at. Probably shouldn't be using a 100-foot station. You should probably use a closer spacing of your measurements. Maybe even down to a foot with a gyro survey. So this is a recommendation that we published in the paper, and it says for wells that are 8 to 10,000 foot deep, you should have a dogleg severity from zero less than a half a degree from 0 to 1,500 feet, less than 1 degree from 1,500 to 25% of the depth of the well. 1 to 2.5 degrees dogleg severity from 25% to 50% of the well depth, and then 1.5 degree from 50% to 75% of the well to kickoff point, and then it's increasing versus depth, 2 to 2.5 degrees from 75% of the depth to within 50 feet of the pump, and then from 50 feet above the pump to the kickoff point, assuming the pump's probably set to kickoff, less than 1 degree. Now, where did this table come from? It came out of some of the predictive programs by using no more than 200 pounds of normal force acting on a 25-foot section of the rod. So the assumption is that, well, we can probably withstand control with rod guides up to 200 pounds of force over a 25-foot section of rods, and we calculate the maximum dogleg severity. So that's where this table came from. This is another well. This is a well where the pump sat out in the horizontal. Now, when we first started seeing pumps out in the horizontal, I said something like, well, how does it pump? Because the pump's on the side. And then someone reminded me that the pump pumps by the pressure below the pump, opens a valve, and the pump valve closes by pressure, fluid trying to flow back, and it checks closed. So the pump just pumped fine in the horizontal without any kind of special treatment. But what these operators found, is that when you put the pump, based on experience in the Austin Chalk, if you put the pump out in the horizontal section of the well, you have 2 times as many failures as setting in the vertical section of the well. If you set the pump in the curved section of the well, then you have 3 times as many failures. So that's what we found. Now this pump card right here appears normal because the true vertical length of the rod string would weigh 13,460 pounds, and the TVD weight is 12,836 pounds. There's an extra 600 pounds of rod load that's not being measured at the surface, and if you don't use the way of the rods that's true vertical, then you're going to have your pump card shift below zero by subtracting out too much weight. So you need to account for the true vertical way of the rod string when you use it in the wave equation. And so here's the same data, not corrected right here, and corrected, and so this pump card looks normal. But if you don't correct it, it's going to shift below the zero by this extra weight of the rods. Now the height of this pump card is the height of the expected based on the pump intake pressure. So this height compared to the expected height is equal. But in this well, this well is a well near Durango in a deviated wellbore, and this well looks like it has a rhinoceros horn on it. I guess a rhinoceros horn is a description. And the operator, and we got out the well. The well was roaring like a lion, and I said, "What's wrong with this well?" And he said, "Well, it's crooked." And I said, "I've never heard a well make noise like this." He said, "Well, the tubing is sliding along inside the casing, and that's making the noise because of the friction between the rods and the tubing." And I said, "What do you do?" He said, "Well, the first thing we try is rod guides, and if that doesn't work, we try co-rod, and if that doesn't work, we run co-rods with polyline tubing, and that takes the rhinoceros horns away, and it stops roaring." So this is a little guideline here for polyline tubing at different temperatures. Used to be that it was just only worked at low temperatures. Now there's different types to use, and when you have a rhinoceros horn, probably the only thing you can do is due to mechanical friction, is to use some lower friction material to remove the mechanical friction. So this is just an example where it can't be fixed because it's so crooked unless you put in a material that reduces the friction. We've talked about the true vertical way of the rod string. You need to make an adjustment for that. If you set your pump below the kickoff point, you tend to have a higher failure rate. The experience has shown that it's 3 times more in the curved section of the well. It's 2 times more in the horizontal section of the well. If you want, I can send you the reference for that. If you email me, I'll send you the reference for that. So this is the ending slide here. The pump card represents the load that the pump applies at the bottom of the rod string. But if there's other mechanical forces applied along the rod string from the surface down to the pump, the wave equation doesn't know typically how to remove those forces, and they end up at the pump, and the pump becomes their trash can for unaccounted for forces. We've talked about mechanical forces. We've talked about the true vertical way of the rod string. We talked about overtight stuffing box, severe dogleg, mechanical friction forces. All these forces impact the measured surface loads. They impact the downhole stroke, the horsepower, plunger velocity, rod loading, and along the rod string. So what we're doing is Echometer's involved with a special project through a group called ALRDC, Artificial Lift Research and Development Council, to build some downhole load cells. And our plan is to put these load cells in the rod string above and below dog legs, and measure the actual loads, and then use that measured data to determine how to modify the wave equation to actually calculate the mechanical friction be applied downhole. And so that's what we're working on. Kind of a volunteer project. We've got the first prototype built. We're going to run it in a well fairly soon. So that's kind of where we're at right now. Any questions or comments? Gustavo, I guess you're doing the questions.
Yes. Yeah, we have a few questions here, but let me start with we have one question says, does sticking damage the rods?
Yeah. That's a good question. If we go back and look at this right here, this is a well that had this original shape right here, and so this backward shape represents mechanical friction calculated at the pump from a force of 7,000 pounds acting at 2,700 feet. The friction force, so that friction force right there, and there's like 7,000 pounds. It's at a depth of 2,750, and when they ran the survey, the wellhead inspection report showed that there was a wall loss of 50%. So yeah, rods on tubing will rub away material, and this shows that. So yes, absolutely causes downhole damage to the rods and the tubing, and an increased failure rate.
Good. If you can refer to slide number 9 or 11, it's the same. So the question is, why does the downhole is plotted below the FO from the fluid level? Yeah.
Okay, so this line right here, the load from the fluid level and the maximum load is calculated based on the pump intake pressure being 0. And so if you have 0 pump intake pressure, you have to have more lift. But if the pump intake pressure is high fluid level, then you have to lift up less load because the well is helping lift up a portion of the rod. So the difference between this point and that point is the lift provided by the intake pressure from the fluid level. That's why this line is above. That's why this line at 0 pump intake pressure is higher than this line right here at the pump intake pressure from the fluid level shot. Is that your question?
Well, I think he asked for the loads below the FO.
Well,
actually, if you go to the lower.
Right, because this is when you the mechanical when you this we're adjusting the damping factor, and so we'll show this example here in a minute. But when you increase the damping factor from the top on the upstroke, it makes this line go down, and if you make the damping factor too high, it's going to push this load line below F where it should be. And so if you have the damping factor just right, it's right at the fluid load line from the fluid level. So if we go to an example here, here's this well right here in TAM, and if I go to the damping factor, it's called pump card analysis, and I'm going to move it right here, and I'm going to increase the damping factor on the upstroke and see how it's going down as I go up, and see I just keep on increasing the damping factor. So when I get the line fairly flat, I'm going to stop adjusting it. And if I increase the damping factor on the downstroke, it's going to go from the bottom, take away from the bottom. See how it crushes it from the bottom. But this is data from the PRT, so the PRT collapses on 0, data collapses on 0, but you're still crushing it from the bottom.
Good. Yes, we have some complementary answers from the participants, like saying that the dyno card loads might be below the FO line when the fluid level is not picked correctly, or when they have the wrong pump size. Yeah.
So if this load line was flat and the FO from the fluid level line didn't match up, then that could mean that the fluid level could be interpreted incorrectly. It could mean that the plunger size is the wrong size.
We have another question from Rinzi. It has a loss of a stroke on a pump car versus surface car is considered under travel. I kind of answered that one.
Right. So this is before this. We're showing. I think we're showing that. No, it's right here. Let's just go there. Well, okay. So when the pump stroke is less than the surface stroke, that's under travel. So this car, the entire pump stroke is lost to stretch. So that's severe under travel, and that's due to downhill sticking. And this one, the pump stroke is much less than the surface stroke due to, again, mechanical friction causing under travel. Okay, and this one right here is another example where we remove the mechanical friction as black line. Now you have a much longer stroke, but still this pump stroke is less than the surface stroke. So normally the surface stroke is going to be longer than the pump stroke unless you're pumping fast. We have fiberglass rods and you have a lot of over travel due to the elastic behavior of the rod string. So normally when you pick up loads, you're going to lose surface stroke to stretch. That's normal. And so if we go into this one right here, this is a plot. The plot of the surface stroke in red, and the green is the pump stroke, and the pump stroke still is less than the surface stroke due to, again, under travel rod stretch.
Right. We have another question. When you were talking about the paraffin treated well,
right?
Do you use hot oil or hot water? Do you also use a paraffin solvent?
That's a great question. In fact, these two data sets came from the same company. When this data was collected, it's been about almost 20 years ago. There was a big discussion in industry about hot oil or hot water, and a lot of companies would take the hot oil from their tank and from their tank bottoms where the paraffin would collect, and so they would take the oil that's saturated with paraffin and heat it and put it in a well, and that would cause the new well to have paraffin problems because the paraffin was saturated out of the tank. And so there was a big push then to stop using hot oil because you're moving the paraffin problem from well to well because the paraffin the problem was in your tank. And so they started saying start using hot water because there's more molecules of water. You can get the heat deeper with hot water. But the hot water didn't work because this was hot water here unless you put a paraffin solvent in with the water. So still they still had problems when you're using only hot water, and probably not enough treatment. But this is a well treated with hot water. It still has a paraffin problem, but they weren't using a solvent along with hot water. So if you can either use hot oil that doesn't have any paraffin in it, because then it has room to absorb the paraffin as it moves in the well, or you can use hot water with a crystal modifier or a paraffin solvent. So those are that'd be my recommendation. But you shouldn't use hot oil from the bottom of the tank for sure.
Okay. Thanks. Before going to the next questions, I'm gonna just bring the last topic back on the under travel. It's a good comment from Joy saying that a bad rod string design, especially with fiberglass rods, a bad rod string design can cause under travel.
Yeah, excessive under travel. Yeah, if you have a big pump, you can cause excessive under travel by putting a too big of pump, or putting a fiberglass rod string in and going slow with a big pump, or a really rod string that's small that can stretch. So yeah, all those can cause it. Good comment.
I have another question from Andres Solano asking, why does the software not consider the rod guides in the rod string and pump section?
That's a good question. We've never really put the frictional forces in the there's two reasons. We just haven't really ever done that. And when I started looking at rod guide materials in a long time ago, between 1980 and 2000, worked for Emerald Hess. I'd go look at wells that had rod guides in them, and I wouldn't see any increase in the load. So I didn't think that rod guides created that much additional friction. In fact, they don't create much additional weight. They don't create, if they're not too abrasive, they don't even show up. That's what my experience has been. Now, if there's a lot of abrasion, they can show additional friction.
Okay. We have another question from Joy. If you can refer to slide number 24, I think you were, and he's asking, wouldn't you see the sticking point on the downstroke also?
Right here. This one doesn't show it that. Let's go back to, yeah, so this slide right here kind of, that point right there, the load kind of decreases, and so you could say, well, maybe it is in the pump because you see an additional friction on the downstroke and you see this additional friction on the upstroke. Yeah, the pump doesn't stop. If you go look at it, you don't see the pump stop, so I don't see the friction force on the downstroke. So if it was sticking in the pump, normally you'd see it at the same place, both on the upstroke and the downstroke. But yeah, I've wondered about that. If that additional friction there is that friction that we're seeing up here, but I don't see a spike. So
we have a question on slide 28 about that. Is a comment and a question. Say, appears the well was drilled with a lot of dog legs, and how do you fix this occurrence? And we have a comment replying to that from Andres saying that maybe increasing the number of rod guides, and it can be used as design software like Roadstar to know the specific points.
Well, you have to take away the mechanical friction. So if you there are different kinds of rod guides. Most rod guides have some reinforcing in them that makes them abrasive. Some rod guide material is slicker. There's a new material that's more expensive called polyether ester ketone that seems to be slick. But if you're trying to remove friction, the only thing I know that has actually worked in my experience in the past has been polyliner. It's a polyethylene liner that is slicker versus more friction. So you don't remove friction by putting something in the well that has higher friction. So the real answer to the question is don't drill dog legs. So I mean that's too late. We've drilled 100,000, tens of thousands of horizontal wells where the push is to reduce present value, and we've drilled wells that are going to be long-term difficult to produce because of crooked dog legs up in the top 3,000 foot of the well depth. And so that in my view has been a mistake driven by economics that probably could have been avoided easily and not too costly. So you might want to read the second paper if you want to know more about that thought.
Okay. Well, on slide number 33, if you can go there. Well, there's a number of slides with similar.
Yeah, right there.
Right there. Were those dyno cards collected using a PRT? That's a question.
That's a good question. Now let me go back. See this data right here. This is the same well acquired the polished rod transducer. And so what you see is that this extra mechanical friction is all on the upstroke, but really it belongs half on the up and about half on the down. So this pump card should be shifted below zero if you had used a horseshoe load cell. But the polished rod transducer, the way it gets to zero offset is it sets a pump card on zero. And there's no way to move the pump card below zero with the current software. Maybe future will fix that. But anyway, this pump card sits on zero, and it tosses all the mechanical friction into the upstroke loads and makes the surface loads higher. So this is a PRT, and this is a horseshoe load cell. And so the horseshoe load cell are the actual loads measured at the surface, and then it calculates from these measured loads down to the end of the rod string, and this is the resulting shape at the end of the rod string. So this is horseshoe load cell data, and this is PRT data. This is before, and this is after the rod part occurred at the pump. So this is a rod part at the pump that you couldn't see as it should be a flat pump card. You can't see it's a flat pump card because this mechanical friction force at 1,300 feet from the surface calculates this weird shape. This is the friction force required at the pump. No, the pump load force required at the pump to create that force at the surface.
Just to stay in the same point, can you have a Walter who's on this point asking if you can clarify that about the PRT setting the pump card at 0 loads?
Okay.
Is that how it determines surface load offset?
Right. So on a horseshoe load cell, the horseshoe load cell is like a bathroom scale, and before you step on it, you adjust it so that it reads 0. That's what a horseshoe load cell does. And so if you were to step on a bathroom scale that was measured with a PRT, it might measure your weight as half of what you actually weigh, and you'd have to tell it, well, here's this offset. And so the 0 offset comes from you moving the dial to 0 with a horseshoe load cell, like a bathroom scale, but there's no way to move the 0 on a PRT. So the thing that we know is that on the downstroke, that the pump card should be set on 0 if there's no mechanical friction. The trailing valve is open. So this should be 0 if there's no mechanical friction, which there is, and the trailing valve is open. The trailing valve is open right here. So the TAM software, TBM software, by setting the pump card on 0 with the PRT, determines the 0 offset, and that then determines the loads at the surface. It works extremely well when there's no mechanical friction. You know, I've got examples where the measured load with a horseshoe load cell on average is within 25 pounds or 50 pounds on average of the PRT measured loads, but those are typically wells with no mechanical friction, vertical well.
Okay, thanks. Next question is regarding slide number 52 on that rhino car shape. It's just to clarify if you mentioned that. Did you say the rhino well also have an anchored tubing?
I have to go look because I don't remember. I don't know, but the tubing, the well was roaring, and the rods were pulling so hard on the tubing that it caused I was looking in the bushes for a lion. I mean, it was like a real lion was out in the woods, in the desert, roaring like he's going to eat you, and it sounded like a lion. And so this noise here was from the rods rubbing on the tubing and the tubing rubbing on the casing. It was unbelievable. I've never heard ever. And the operator said, "Yeah, this happens all the time on these wells." And the only way to make it stop was to remove the friction. You know, they tried rod guides, then they tried co-rod, and then they tried polyliner. He said once we do polyliner with co-rod, then they stop. The line leaves and the horn goes away. But I don't have any data to show that. I don't have any data, just the word from the operator when we were at this well.
Okay, we have another question from Borg Phone. And the question is, if there were distributed rod tubing friction, how would that show in the car? Or are you able to account for all the friction at points location, like at the stopping box, sticking points, or high dot?
Right. So when you look at the deviation wave equations, the wave equations developed for deviated wells, they assume that there's a drag coefficient based on the perpendicular force or the normal force acting between the rods and the tubing. And that's a continuous force all along the entire rod based on the angle and the force of the way the rod's down to that point. So that force is something that they can model. But so far, the data that I see, often that force isn't a big deal. The force that I see that shows up a lot is this mechanical sticking force from a dog leg. I'm not saying that there's not rod rubbing on tubing, because that's what they put in the deviated wellbore models. They put that in. But the forces I've been showing you are from forces that aren't modeled that way. These forces are forces at a point along the rod string. We don't know the magnitude of the force or the location of the force typically. And just recently, we've realized that the slope of the stretch of the rods is starting to tell us where the force is and the magnitude. So those two examples I showed you are trying to show you where the force is. It's related to a dog leg, not just friction between the rods and the tubing because it's laying on the side. So some studies have been done in the Bakken by a company, Emerald Hess. They ran some couplings that were made out of nickel and scandium and tin, I think. The couplings are very expensive, but they're material. They're called met something. I can't remember the rest of the name, but they're very friction resistant. So they cost like 10 times the regular cost of coupling. But when they ran them in the wells, the damping factor dropped. And so I said the damping factor drops they said about half. What they run an entire string of these low friction couplings. And so that meant that the wave equation already somewhat models, or has been modeling, coupling on tubing friction. Because that's a friction, but it's not really a function of velocity. That's just a drag friction. That's just a drag coefficient friction. So this is really complicated, and that's kind of why we're working on this project to ALRDC to build this downhole load cell, because we want to be able to measure the mechanical friction forces and then be able to calculate them. When we did the Sandia data where we measured downhole forces, all those wells were vertical wells with really nice well bores, no dog legs. So this project we're working on is to try to measure mechanical friction, identify the location, and then be able to come up with a method to calculate it. And there'll be two parts. One part's going to be this related to the dog legs, and another part's going to be related to the drag coefficient. So that's a long answer.
Okay, we have a couple of more questions. One question from Chris is, the proper damping factor, that's a good one. The proper damping factor shall be always matched with the FO from the fluid level or from FO max. And the fine tune always is manual.
Inside TWM and inside TAM, there's a reset button that defaults the damping factor. And what we've found is over 30 years of experience that you can estimate the damping factor based on the well depth and be reasonably accurate when there's not a viscous crude in the well. And so normally when you don't have high viscosity fluids, then the damping factor, just by going into the TAM software, let me just show you an example here. If I bring up TAM right here, and this is the same example, if I go into pump card analysis and I click reset, that reset button right there is going to reset the damping factors based on depth. In this well we have 10 API crude, and it's much more viscous than the default, but when I hit the reset button, the damping factor is not correct because you can start to see the concave outward shape of the surface, the pump card. And so the answer is that for typical wells where there's not a lot of fluid friction on the rods, the default method, hit and reset, works great. But then when you have extra friction, you got to use your your eyeball, in my view, to adjust it. Now, there are some software programs that do some automatic adjustments, and that might be an option available. But the only automatic option we have so far inside of the TAM software is when the pump horsepower is negative, adjust the damping factor so the pump horsepower is not negative. And that usually happens when you have a rod part. If the rod part occurs and the rod string is shorter than it should be, then the damping factors will be too high. We'll take out too much damping horsepower, and then the pump card will have a negative area, and we've added an option to automatically calculate the pump horsepower to be 0. Now, we could someday put in the TAM software, make the upstroke loads be flat, and we could do that, but we just have never done that. So there's not an option available to automatically in the TAM or TWM software to automatically adjust it when the defaults don't work.
Okay. We have one last request from Joey asking if you could talk a little bit more about rod failures when pump is in the horizontal area
Okay.
compared to the pump in the core.
Right. So Norm High and I presented a couple of schools in Oklahoma City as part of the suck rod horizontal schools, and we had some discussion. There's several papers written, and Harbison Fisher was the one that came up with their experience, and their experience was that if you set the pump, and this is assuming that the well's doesn't have severe dog legs, above the kickoff point, if you set the pump above the kickoff point, then the well's going to have a normal life, whatever normal represents. But then if you set the pump in the horizontal, the pump will still work just fine, but you'll have 2 times the number of failures that you would if you had the pump above the kickoff point. But if you set the pump in the curved section well bore, then you typically have three times the failures. And I have that reference. I think that reference is probably in the paper that's on the cover slide of this PowerPoint. So there is a reference for that. It's in the paper. If you can't find it, I can email it to you if you just email me. A long time ago, well, 20 years ago, I was working with a technician that had wells in the Cedar Anticline up in Montana, and they had been bought. This dude bought it. Continental Resources had bought that field, and the owner of Continental Resources told the technician and the operators of that field that he paid a lot of money for that field, and he wanted to get every drop of oil out of the wells, and he wanted all of his pumps in the horizontal. And I didn't know that, but I talked to the technician one day, and I said, "You've been sending me a lot of data, and these wells have a little extra friction." And he said, "Well, they ought to have extra friction because every pump's set out in the horizontal." And I said, "Well, the pump's pumping just fine. I would expect to see more problems with the pump." He said, "Well, they pump fine. It's just that we have more friction." And then 6 years later, I was teaching a class in Tulsa, and many of the engineers, several of the engineers from Continental Resources were there. And I said, "You guys, I'm impressed. You guys are here for the class, and you guys run all your pumps out in the horizontal." And they all looked at me like I was crazy and said, "We don't do that anymore because we couldn't afford the high operating cost." And so that's just an example of the idea of running a pump below the kickoff point. You increase the friction, you increase your failure rate, you increase your operating cost. You can do it, but you have to pay. And that's just, now Echometer has a product that we sell that Brian Elthorpe takes care of, and it's called the Ultimate Production System for Suck Rod Lifted Wells, where you run a tailpipe out in the horizontal and let the well flow the fluid up the tailpipe up to the pump and set the pump in the vertical. And that's something that idea was driven by the high operating costs of setting the pump below the kickoff point. And so we have information on our webpage about that, and that's another option that you might be able to try is don't set the pump in the kickoff point if you're experiencing high failure rates, or use some kind of friction device that reduces friction, like polyliner, or maybe co-rod with rod guides or slick rod guides. But anyway, once we draw the well down, it can be costly to operate if you have to stick your pump out in the horizontal. Any other questions, Gustavo?
We have one more. Don't fully understand, but I'm going to read it as it is. From Chris says, regarding the unaccounted friction ratio, the max value is related with the mechanical friction or also fluid rod friction?
Right. That's on slide 52. And so if we look at slide 52 right here, this idea of unaccounted for friction, and so the pump card in this example here should just go up to FO from the flow level. So the pump card should go to right there, but the pump card is a lot higher. And so this friction is from some other source, and I call it unaccounted for by the wave equation. So if the wave equation knew how to handle this surface loads with rhinoceros horn, then the pump card would look perfect, and it'd go right along FO from the flow level on the upstroke and go down to 0, and there wouldn't be any unusual shape. But since there is friction, that this wave equation that's being used in TAM and TWM doesn't know what to do with, and no one knows what to do with this stuff, then it's not accounted for by the wave equation. So we're comparing the total height of the pump card right here, and that height right there, to the height that should be, FO from the flow level. And that ratio is 2. It has twice as much friction than the actual, twice the loads than what it should have. That's the unaccounted for friction ratio.
Well, and apparently that was the last question. Thank you very much.
Now, Walter said that the metal, the sucker rods are tough met, and Anthony said Materion. So that's the material. Yeah, they're pretty low friction couplings. All right. So the next thing I thought we'd do for the next 26 minutes was look at some examples. So I'm going to pull TAM over to the top of the computer here. All right. So let me close this right here out. And on my computer, if I say pick a well, and I'm going to fill the full screen. Hopefully that's not a problem, filling the full screen. And then pick a well, and the what I have on my computer is, if you go to the Echometer webpage and you download these examples and you say install them on your computer, it's going to create a folder called Echometer Online and a subfolder Mechanical Friction, and this is the second Ask Echometer presentation we've done. And then there's 1, 2, 3, 4, 5, 6, 7 different examples of mechanical friction problems. And so we've looked at this one right here, which is the well that in the background, which is called Damping Tin API. And someone, I think, wanted to know, I don't think I have the rhinoceros horn here as an example, but this is the stuck pump, the one that's stick, the stuffing box friction, and the unaccounted for wellbore friction. So I'm going to go to the stuffing box friction one first. And the reason for that is I want to show that this is the overtight stuffing box here, and this is the one that's not overtight. And so when we go to the overtight stuffing box, and we click on the pump card analysis button, what I want you to notice is that the pump horsepower here it's about 7.3, and that's with the default damping factors that we've set by. Well, we went into pump card analysis and we hit the reset button, and that gives you the damping factor on the upstroke and the downstroke based on normal fluid viscosities and assuming a vertical well. And then we have this stuffing box friction in the TAM software, and the stuffing box friction is around 500 pounds. And so Ken had a calibrated crescent wrench. He put exactly, that's kind of a joke, 500 pounds of stuffing box friction, and that then makes this pump card look a lot like the one. Let me show you the one before. So they look very similar. So this pump card and the pump card with 500 pounds of stuffing box friction look almost identical, but you really can't tell that there's all this extra mechanical friction because you took it out. Now I'm going to go into annotations and remove this annotation called FO from the fluid level. So I'm going to click on annotations, and there's the load line calculated from the fluid level 3,910 pounds. I'm going to remove that and then say OK. And what I want you to notice here is this little transition isn't quite done perfect, because it has to do with how we remove this mechanical friction force. What we said was that when the rods are moving up, take away 500 pounds, and the rods are moving down, take away 500 pounds. And then run it through the wave equation. So this piece right here is that little funny shape is because we didn't quite transition the loads correctly from plunge velocity moving up to velocity moving down. That's something that we may need to fix later on, but it worked pretty well. I mean, it does a decent job on removing that stuffing box friction. So that's one of the things I wanted to show you. This also shows that vertical line. You see a vertical line on your surface card when you have excessive mechanical friction near the surface. That means that there's no rod stretch, and there is what? A change in direction of friction based on the change in the upward versus downward velocity of the polish rod. So if we go to the analysis plot and look at the analysis plot and look at here is the position of the polish rod in red, and if we put the load at the polish rod load, there's no vertical line right there. Okay, but this becomes a vertical line if you let me plot this velocity here, polish rod velocity. So there's a polish rod velocity. If you turn this into, instead of being plot versus clock time or in terms of seconds, then you plot it versus polish rod position, then that little thing right there that, well, it's not instant. It starts right about there, and that time is 6.1 seconds, and it goes to right about there, and that time is about 4/10 of a second. So the friction reversal occurs over about 4 seconds of time, and it becomes a vertical line since it's at the top of the stroke. So let me show you what happens here. I'm going to change this from the elapsed time to polish rod position, and see how that vertical line occurs right there. That's the reversal of the friction. It's resisting the load. It's a friction on the rods, and when the rods change direction, it has to change direction of the friction. So that's that vertical line. You should expect to see that if the friction's near the surface, or if it's being released, you should see that. Now, I'm going to pick another well. Does anybody want me to look at a particular well?
We still have some time.
I've got 20 minutes. So the one I want to show you is the let's see, I think it's stick release upstroke. Okay, now this one right here is the one we talked about as a little spike. And so if we go back and look at the surface card and the pump card, and this little thing right here, I thought that's at first I thought, oh, that's not much. It's not much load, but if you look at it, let me show you this right here. If you watch the pump and you watch the plunger over here and the polish rod, the bridle, the carrier bar, watch what happens when you get to right about here. Right there, the trailing valve stops, the plunger stops. And then as we move up, right there, the polish rod moves up a lot. See, the polish rod right there moved up a lot. That's like 20 inches of position change. And the load, look at the load. See, from here to here is like 20 inches of stroke. And the load changes a lot, but the pump's still in the same place. That little bitty thing right there is a huge change that's the tug of war I talk about. So from here to here, the polish rod moved up 20 inches from 120 to 140 and applied the spring constant to the rods by stretching them. And the spring constant is probably more than 214 because it's not at the pump. But the plunger just stops. So the plunger stops and the polish rod moves up, and that's the giant tug of war, and that makes this little spike. The wave equation draws that little spike, which it doesn't look like that, but that's what the wave equation draws. And so when you get to the very top here, right about there, then when the plunger takes off, see the plunger's moving there, and the polish rod's not moving at all. It stored all that 20 inches of stretch as energy in the rod string, and so the release of the energy from here down to there is the plunger moving when the sticking force down hole has been overcome. And so this is a to me a very interesting example because this is much steeper. That means it's sticking up hole. It's steeper than this, where it's 214 pounds. This is 214 pounds over here. Look at the presentation. And then right there we overcome the sticking force, and it moves. Doesn't move very much on the polish rod, but it moves. Geez, it moves 30 inches down hole, which is the release of that stretch causing the plunger to move. Now this is a vertical line. See this vertical line here? That means that we're overcoming some downhole sticking force that's occurring downhole. And so the idea of looking for a vertical line on the surface card at the top and bottom of stroke usually indicates that you're overcoming some kind of mechanical friction force. As the friction is being overcome, released, the loading is dropping off as the friction is released. Now, if we go look at the analysis plots, so here is the pump load, and let me draw two of these so you can see two. So there's that plot right there, and I want to plot on this one the load, the polish rod load. So here's the polish rod load right there. And so as we move on the upstroke right here, we're moving on the upstroke. Okay, right now the trailing valve opens right there. The standing valve opens, and the trailing valve starts to move, carrying the fluid load. And right there, we start to stick downhole. The plunger stops, and the polish rod moves up and moves up and moves up. And right there, we overcome the sticking force. And the polish rod doesn't move much hardly anymore, but the plunger takes off and moves up another 30 inches or so. So that's the relationship. You see how this motion here from right here to right about there is the surface loads change significantly. Okay, but when you look at it as a surface card, rather than in terms of time, the time doesn't seem that big a deal. It's just release of load versus time. But when you look at it in terms of a stroke, position, polish rod position, you see this vertical drop in load. So when you go from this release, you see this vertical drop in load, which is indication of a release of downhole friction. Okay, so that's kind of a interesting. To me, this is an interesting relationship between what's going on right here and this portion of the surface dynamometer card. It's an indication of downhole sticking, friction, release of friction. Now, the next one I want to look at is not the stick, but not the stuck one. This one right here. Okay, this is the one that we had the deviation survey on, and there's several examples here that show different things in this data set. And these are sampled at a very slow speed. These are high speed. So there's 480 data points per second that we sampled at. And so this data was acquired with the Horseshoe load cell. Okay, and so here's our Horseshoe load cell data, and notice how the loads are going below the zero load line by the excess friction on the downstroke and going above FO max on the upstroke. If we go into annotations and turn on FO from the fluid level, then this is extra friction up here, from here, the black line to that line, and then this is extra friction on the downstroke. Usually, in my view, the friction on the downstroke is usually higher because you're moving opposite to the direction of flow, and the friction would be less on the upstroke. This is a little bit less than this because you're moving with the flow of the fluid on the upstroke. So that's kind of how I explain to myself why this is less than that. And notice that that point right there looks like it's probably correct because it's the trailing valve closes right there at the zero load line. That looks pretty good. All right, so now what I want to show you is if I go to the field view here and look at this, and I want to overlay on top of this data here the data collected on this well at the same time. Here's the same time. This data is collected with the Horseshoe load cell. This data is collected with the polished rod transducer. And so if I go to the annotations screen here, there is a button here that says previous strokes. And so if I click the previous strokes button and I go turn this one on, then this is comparing two strokes at the exact same, well, not within the same 30-minute time interval. That we have this stroke right here is with the PRT we're overlaying on top of the stroke that was acquired with the Horseshoe load cell. And there was a question during the class about what about this zero, the zero of the PRT data. And I think this was probably a good example of showing how this data, the zero offset works. And so let me drag this out of the way. It's still calculating. I shouldn't have touched it. When you sample at 480 samples a second, even if you have a very fast computer like I have, it still takes a long time to process the data. So that's one of the disadvantages of sampling at high speed. All right, good. All right. All right, notice here that this pump card sits on 0. That's because that it's acquired with the PRT. And notice that the PRT loads are higher by about, looks like that loads almost 40,000 pounds. That loads 36, almost 4,000 pounds. So this distance from here, that's about 4,000 pounds. So the shift of these surface loads are about 4,000 pounds due to the PRT loads having to set on 0 to get the zero offset to calibrate the loads. Well, they calibrate it by making all the friction be above the zero load line. So the blue line is PRT data, and the black line was the Horseshoe load cell data. And this shape here, that shape there, that slope right there, all of those slopes are created by the wave equation trying to calculate that friction from the dog leg at 1,350 feet down at the pump. And that's where that's coming from. Does anybody have any questions or comments about that? Carrie Ann, you want to summarize? We'll talk about this. We can.
So the recorded video of this session is going to be available on our website on Friday on our Ask Echometer page. And I put a link out there. Let me do that again real quick. You can go out there now to download the PDF presentation and also the TAM example data that Lynn is showing you guys right now. And we also have last week's session too, if you want to go and watch that. Next week's session is going to be on plunger lift, and we hope to have a schedule up for the next several weeks so that you guys can have a better idea of what we have planned. And if you have a suggested topic, please ask us to create a session on it. So that's why we're here, and we want to get you the information that you need. And we appreciate all of your questions, and if you have any follow-up questions for Lynn, we welcome your calls and emails. If I have you on the registration, then I'll go ahead and send you a link for next week's session automatically and from here on out. So, we certainly appreciate your time today, and we look forward to seeing you all again next week or in future sessions.
All right. Well, thank you guys very much. Hope you enjoyed the presentation.
You guys have a great week. Thank you.
Thank you.